So here we can combine the change in flux and our old equation for the force on a wire that is carrying a current, and we can actually come up with an equation there that goes for the total force that acts on a wire in our, remember our situation is this, where we're moving it. So if we combine together our EMF and flux and everything, we can actually insert that into, by essentially solve for the current and insert that into that B times I times L and come up with an equation for that. I don't know if you need, what? What? Oh, okay. Y'all know I'm old and don't hear well, right? Y'all know this. So then everybody has masks on and I can't tell who's talking and it's all mumbled. Huh?
Over there saying what?
Okay, so if you come back, you can use this to come up with what the actual current will be using this and Ohm's law. So I'm not sure why you actually need this next equation. So it's up to you if you want that final result. I don't like final results because I feel like I'm always going to end up applying it to a situation that I shouldn't have applied it to. So I like to kind of figure everything out right from the beginning. So if I had a problem asking me for the force it took to push something like that, I would probably just start with the BIL and then look at the rate of change of the flux in a single loop and go through and figure out the induced EMF and then look at the resistance and all that kind of stuff and try and solve it that way. Okay. Next, you can look at this here. We can actually go ahead and calculate the mechanical power. Power is force times velocity. If you look at that, we got the force from the last page and then times velocity, and you end up with B squared, V squared, L squared over R. If we instead try to compute the power through the light bulb using the electrical power, which is P equals VI, which if you combine with Ohm's law gives you I squared times R, you can substitute in for I and then times R and look at the results you get. So remember when I said that magnetic fields do no work? You see this? Every bit of energy put into that circuit can be accounted for just by the force it took to move that rod. So you are getting absolutely nothing from the magnetic field, right? It's like the broom, right? Maybe the end of the broom's pushing the dirt across the ground, but it's all your work. You're the one pushing the broom, not the broom. The broom isn't doing the work. Okay, so it may like get transferred through the magnetic field, but it's not the magnetic field doing it. The magnetic field is not converting that energy over. Okay, does that make sense? Good. Generators. Here, the idea is to simply spin, either spin a coil near a magnet or spin a magnet near a coil, and that changing flux to it, as long as you keep it spinning, continuously creates a changing voltage. All right, and it's an alternating voltage. You can then hook that up to something, a battery, or directly to something and power it. This is how your generator is going to work. You get some sort of mechanical input. If it's like a car engine, that mechanical input is ultimately comes from a chemical reaction, right? Where you combust the fuel inside the cylinder, which pushes the cylinder, which turns a crankshaft, which then you could then ultimately spin a magnet near some coils and get that. And that's what your alternator is. The alternator is the generator. It gets its mechanical energy from the engine, right? It's actually hooked up to the belt on the front of your engine typically, and it spins that. And if you ever look at an alternator, you can see all the coils of wire in there, and then it spins everything inside of it. And that's how your car generates electricity for your radio and everything and to recharge your battery. If you're looking at a house generator, same sort of thing. Internal combustion, it just has an alternator in there, and that's its main purpose. If you're looking at a power plant, then it depends on what it is. If it's a dam, like that, you know, it lets water go through that comes down and spins the magnet. If it's a coal plant, it, you know, burns the coal, uses steam to go through and push it. But it's always about doing that. Even the nuclear power plants, they just use the nuclear material, right? The fissile material, like uranium or plutonium or whatever they're using, and they use that heat to create steam, and then they push that through a turbine, spin a giant magnet, create electricity. I also did notice that we have obviously fully covered everything we need for time travel, since we have now fully learned about capacitance and flux. Obviously, we need a Mr. Fusion, but once we get that, we should be good to go. And again, we even know how to make it generate the 1.21 gigawatts of power. Or we need a bolt of lightning. We have to pick up a DeLorean. We need the stainless. We don't know why we need the stainless steel, because he gets interrupted. So we generate electricity. The type of electricity you generate looks like this. It is alternating. So you get an alternating voltage that's going to push and pull charges one way then the other, back and forth, and it will do so in a sinusoidal manner. Here you can see what it's going to depend on. N times B times A, that's all dealing with your flux, and then the actual sinusoidal nature of your changing flux, which would, I imagine here, it's going to change within, is going to create that changing electric field, which then creates a, well, for you math people, you then have to integrate that to get that right there. So anyway, or derivative of it, whatever, and you get that. Okay, so anyway, NBA, omega, sine omega t. Omega would be the angular frequency or the angular velocity of the of how fast it's spinning. Okay, spin it faster, you're going to get a greater amplitude. Here we have an electric motor, where in this case, what you're doing is instead you run it in reverse. Instead of having it output electricity because you mechanically spun it, you input electricity, which causes current to run through the wire, which creates a torque, which causes it to spin, which then you can use to output mechanical energy. So you can convert electrical energy into mechanical and mechanical into electrical, just almost like just reversing the whole process. So disconnect whatever lamp you were using here and input a source, and it can run electricity through it and start that thing spinning. And it's an electric motor. So electric motors and electric generators are actually very similar in concept. It's just which one's the input and which one's the output. Okay? Any questions so far? Okay. Let's go to do a problem before we start inductance. Okay, where is one we can start? So let's see here. Page 812. The light bulb has a resistance. So I guess let's look at page 812, right? This is not your book. Physics. 812. Let's see the picture. There it is. I assume that's the only one. Yep. So we have this light bulb, and we want to come up here. So we've got a bulb, which is just a resistor that emits light. We've got this, and we've got a bar. And what was, oh, I gotta go the other way. What was it pointed out? Okay. So the magnetic field is pointed out. And we know that we have a resistance of 12 ohms in the wire. Oh, wait, in the light bulb, sorry. So resistance of the light bulb, and consumes 5 watts of power. The rod is 1.25 meters long. Let's call that L. 1.25 meters, and moves to the left with a constant speed. So this direction, speed of 3.1 meters per second. What is the strength of the magnetic field? What external force is required to maintain the rod's constant speed? All right, so we're getting a power of 5 watts, right? So some things we can think of: electrical power, P equals VI. We're going to probably need V equals IR. We also need to worry about what the changing flux is. So if we know that we have this level of power and that level of resistance, we should be able to then, we should be able to go through and mess with this some, right? We're also going to have to worry about what the changing flux is, right? So the EMF that is created is N is 1, and then we have the rate of change of the flux, right? So delta flux per time. Now, the change in flux is B times A. We don't have to worry about an angle because we're staying perpendicular to it, right? So it'd be that which is just going to turn into a 1. So it's BA over T. The area that we have is going to be, as this moves to the left, this distance here is velocity times time, right? That's, if we call that distance D, which is velocity times time. So then we know that the actual area here is just BL VT over T, and the T's will cancel. So we're left with B times L times V, and that tells us our EMF, which is what our voltage is. Now, we don't have current, so we don't want current in our power equation. So I'm going to use V equals IR to eliminate current. So this is I equals V over R. So P is going to equal V squared over R. Okay? And then instead of V squared, of course, it's our EMF squared. So it's power equals our epsilon squared over R. Our epsilon is BLV, and it's all squared over R. And so that has to equal 5 watts. And so from there, we can solve for B, because we know L, we know V, we know R, we know P. Correct? So that tells us then that B is equal to PR over L squared. You know what? Let's just do over LV, like that. Square root of PR over LV. And that's what B is. And so we come back over here and we say square root of power is 5 watts times, what was it, 12 ohms? 12 ohms over the length, which was 1.25 meters, times the speed, which was 3.1 meters per second. So that's square root of 60, which is a little less than 8. And it's 8 over, what is that going to be, like 4? So 2-ish. Is that right? One point what? And then Tesla. Okay. Any questions on that? So sorry if you don't like how, but I like to work from the most basic equations I can to make sure it actually fits the situation. Because I know I'm going to look at an equation that you have on some sheet and then apply it to a situation that it actually wasn't derived for. And then that's, you know, I can't tell you how many times I see physics students get stuff wrong because they do that. They take something and they're like, oh, look, all they do is match up and they say, oh, I have this, this, and this equation has this, this, and this, and so therefore I'm going to use it. And then it turns out it had nothing to do with that situation. It was like a totally different situation that it was derived for. So I really do, that's why I quite often tell y'all, you know, you can write down that whole thing or you can learn how to derive it. And I think deriving things works out a lot better for you. All right. So what external force is required to maintain the rod's constant speed? Anybody think they can do that? Take a moment. Don't even look anything up. Anybody think they can come up with what that is? Anybody remember what the force on a current carrying wire is? Yep. We can give you that. So this is part A. Try part B. F equals B times I times L. I'm going to give you a minute. Everybody try. Even if you get it wrong, that's okay. You learn through mistakes, right? What is it? My wife always says something that mistakes are learning's best friend or something like that. So I don't know. It sounds more elegant when she says it, but that's the same idea. Making mistakes is good for, gosh, I can't wear this anymore. Making mistakes is good. So just do it. Make mistakes. It's fine. Oh, Casey didn't ever tell him. That problem the other day we were having issues with was because I put a squared on there and it should have just been not a squared. I squared the voltage or something like that when I wrote down the equation, which is, again, see, that's why you don't write down stuff from memory. You write down stuff from memory and you make mistakes. I did that today in calculus. I'd solved the problem for someone for homework, and then when I reopened it, it gave me different numbers, and I didn't even pay attention to that, and I started just writing down what I remembered, and then the whole problem didn't work at the end, and I was like, wait, hold on, what did I do here? It took me a few minutes to realize they had changed the numbers, so don't do that. In the world of math and physics, comprehension is way better than memorization. And in fact, I used to tell all of my students it was impossible to memorize your way through physics until I had a student do it in AP Physics, and she memorized her way to a 5 on the AP Physics exam. I've never seen anything like it before since, but she sure did. She didn't understand anything. She just spent all her time memorizing every example problem she could. I am absolutely serious. If you asked her a question she'd never seen before, she would be totally lost. She did not. And she would flat out tell you, I don't understand a thing we're doing. I just constantly do problems. She got a 5. Courtney Fee. That's not true. They reuse them. And there's a lot of problems that, yeah. Or am I only thinking of IB? IB reuses them. Are you sure? After so many years, I thought they became eligible again. They're not going to reuse any of the ones in like the last 5 years, but yeah. Maybe I was teaching IB a lot longer than AP, and IB, the kids would go get all the old exams, and a lot of times it would just end up being the same questions on there. Even the same, you could even get lucky and get almost an exact duplicate of a test too. They would do that. But there's still only so many questions you can ask. It would have just been different numbers. She memorized like every situation. No, I have not. Anybody get this? Okay, I don't care. I don't have no idea what the number is. What did you do?
Oh, I did power over velocity.
Oh. Okay, I did not do that. Where did you get that?
Well, because we said force equals BIL.
Okay.
And then I plugged in, BIL is voltage.
Oh, so you like went through and actually plugged that in and derived it? Nice, good. I thought you looked up some equation we covered. Brilliant. All right, so you said F equals BIL. We know B is square root of PR over LV, right? Times I times L. So the L's are gone. But then we have P square root of PR times I. We don't know I. So what did you do to get rid of the I? You used this right here and said I is P over V, square root of PR times, and you said P over V over little v, right? Capital V, little v. And V is that EMF, right? So you said that's the EMF. And then what?
Well, we said EMF equals
BLV. Nice. So we've got square root of PR times P over BL little v squared, right? Then what?
Well, essentially at the end, because at the end I have F equals B times P over BLV times L. Because I didn't have a square root of PR.
You didn't?
I didn't know.
Why didn't you?
1.61.
What did you got 1.61?
So like.
Well, I was following your steps. What did you do next?
So here I got F equals BIL. That's the first equation I have.
Yeah.
And so then I knew that.
So I didn't follow what you just did because you kept telling me yes.
Well, I was a little confused at the square root, but you said like you did follow what I was doing because.
What did you do with the square root then?
Well, I don't know whether you got the square root from because I just got F equals B times I over L.
But this is what B is.
Well, I didn't put that as B. I actually did it with I because then I did I equals P over BLV. And that cancels.
So you left the B in there the whole time?
Yeah.
So then you just plugged in the 1.99 later? Ah, I gotcha. Okay. All right. I'm sorry. I thought you like derived this whole thing down like just using all the original numbers we were given. Oh,
Sorry.
no, but you were close. But I would have probably done something like that. But yeah, you can plug in that. We're back to B, right? Oh, I have B in there again. So I guess if I go back, the B's would have canceled. So I have that B there. That would have been, that would be square root of PR over LV squared times P. And then that B would become LV over square root of PR. So it would cancel. L would cancel, that V would cancel with one of them, and we just get P over V. Longer roundabout way, but yes, there you go. Brilliant. How did you do it? Oh, you did it like the engineering way. Yeah, they like to plug stuff in. I don't like to put numbers in until like I very much have to at the end. Okay. So what was our final answer? So the power was, what was it? 5 watts. And then the speed was 3.1 meters per second. But that's nice, that P over V. It's like we got that the force only depends on those two things. And so what was it? 1 point what? 6.1 newtons. Watts per meters per second, right? A watt is a joule per second. A joule is a Newton meter, and a Newton is a kilogram meter. So it's a kilogram meter squared per second squared times that per second. So per second cubed. So a watt is a kilogram meter squared per second cubed divided by a meter per second, which is a kilogram meter per second squared, which is a Newton. So there we go. Cool. Units work. All right. Any questions on that one? But I like that when you do stuff like that and it just goes down to like 2 little things after all this complication. That means you either really did something right and elegant, or you really did something very wrong. You know, like it's one or the other when that happens. Okay, what is this one? Okay, 23-3, where is that? Referring to 23-3. Anybody know what page that's on? That's 23-4. Is it still this one? Is this 23-3? Yeah, okay, so the same one. And then this says, find the work done by the external force in 0.58 seconds. So is that? So I guess that's the previous one. Yeah, all right. So the work done in that much amount of time. So how do we find work if we have force and we have time and all that kind of stuff? Going at a constant velocity. Think back to last semester. So, okay, so let's write down, this isn't our definition of work, but it's a nice, good working one, right? Force times our displacement, right? F delta x, assuming this force is parallel to that displacement, which in this case it would be, right? The way we're pushing this thing. So we need the actual displacement, which is what? Huh? VT. Okay. And so we found what the force was, right? P over V. P over the speed, right? Times the speed times time. So this is just power times time. We should make sense, right? Because power is work over time. Nice little self-consistency right there, isn't it? And so that's all we have to do. What was the power we had? Five watts times 3. So 5 watts times 0.58 seconds. 2 point something, 2.9, close to 3 joules. Okay, that's part A. What about part B? The energy consumed by the light bulb in the same time. Well, the energy consumed by it is what? P equals voltage times current, right? Which we don't have the current, but we have V and R, right? We have the EMF and R. So this will be P equals, what was it? Epsilon squared over R. So epsilon squared over R. And power is work over time. So this is going to be the work is epsilon squared over R times time, right? Because this equals work over time. And epsilon, we found on the previous page, our EMF was just BLV. BLV over R times T.
It'll be BLV squared.
Squared. Thanks. And we have all those numbers. We could plug them in right now, or we could keep trying to derive stuff, right? And see if we just end up with P times T. You want to keep trying to derive, or do you just want to plug numbers in? We have all those, don't we? We have B, we have L, we have speed, we have R, we have T. So what's B? Let's plug them in. Squared times, what was L? 1.25. Speed was 3.1, is that right? 3.1 meters per second. So and then R was 12 ohms, and time is 0.58 seconds. So what do we have there? 4 times 9. It's like 36 divided by 12, 3. And then 3 times about 1.5. So about 4.5. 2 or 3-ish, is that right?
The final I got 1.67.
So 2-ish then? Did anybody else do that one? Is that what that comes out to be? You sure you squared everything? Huh? You don't have one on your phone? Again? This is like.
Okay, yeah, I got 1.67.
You did? This is like a 9. Yeah. I think so look, this is about a 4 when we square it. This is about a 1.5 when we square it. This is about a 9 when we square it. A little bit bigger than those. And then divide that by 12. 4 times 9 is 36. Divided by 12 is 3. 3 times 1.5 is 4.5. And then we're taking 60% of 4.5. That should be up near 3, right? I think that's got to be a lot better. I think y'all are typing this in wrong.
Well, what I did, I squared the.
0.58.
Oh, 2 point what? 87, so 2.9. Much better, right? Or we broke the rules of physics somehow. I mean, it really pretty much has to be, right? Because that's the work done externally, and that's the work, input to output, assuming this is 100% efficient, that all of it gets turned into light. That light bulb is not 100% efficient though. So I guess it's the energy consumed by the light bulb. It doesn't say emitted as light, you know what I mean? Most likely there's heat too. Depending on what kind of a light bulb it is, will tell you how much of it becomes light and how much of it becomes heat. And then of course, there technically is some resistance in the wires, and there's friction as you push that thing along there. So there's other stuff. It's not gonna be 100% like this. But assuming it was made out of unobtainium and the wires were frictionless and resistanceless and all that kind of stuff. Okay, what's the next one? Okay, we'll save that one for next time because we got like 8 minutes left. So let's start looking at inductance. So I told you before that essentially what happens is you end up getting what is called a back EMF. Since nature tries to stop you from changing flux, when you send electricity into a coil like that, it initially tries to create current going in the opposite direction. Because when you do that, what happens is you send current one way and it starts to create a magnetic field through that coil, right? Wrap your fingers in the direction of the coil, the turns of the coil, and your thumb points out where north is going to be. Well, it doesn't like that addition of flux. So what happened? Did I lose screen broadcasting? Yes, I did. What happened? Yeah, apparently. Oh, I got kicked out of the meeting here. Continue. Sorry. So when you start to add a flux in one direction, it creates a, oh, y'all could see that. You like that? I was trying to make this up for the science department. I don't know. Graphic design stuff. So anyway, when it makes a magnetic field this way, that coil says, no, I don't like that. I want to make a magnetic field going the other way. And so it creates a back EMF, a voltage in the opposite direction that then pushes current back the way it came. So when you first turn on current into an inductor, it acts as though it's a short, like it has infinite resistance, because you turn that on and it immediately tries to push back. What happens when you first turn on current through a capacitor? That's right, it acts like a short. Initially, when you first turn on current through a capacitor, it acts like there's nothing on it because there's no charge on it and all the current can just flow with no resistance. Then as this resistance builds up on there, or as the charge builds up on there, it gets harder and harder to push more charge on there and the resistance goes up. With an inductor, when you first turn current on into it, it has this back EMF that tries to stop you. And so it has a bunch of resistance. But then as that back EMF, as it starts to get used to that new flux, it starts to decrease. And so your current starts to increase and it starts to then act like a short. So capacitors act like shorts at first and then their resistance goes up. These guys act like big resistors at first, and then their resistance goes down and their current goes up. So like I said, they do like the opposite of capacitors. So a lot of things you can do, they're called high pass and low pass filters. Like if you're making a stereo system, you can filter out high frequency and low frequency sounds to go to like different speakers, like the tweeters versus the subwoofers and stuff like that. And you can do that using capacitors and inductors. However, typically, you might as well just use the capacitor because capacitors can be made a lot more consistently. It's hard to make inductors that are always what you intended them to be. Okay, so capacitors, they're a lot easier to manufacture and get, when you buy a whatever size capacitor, it's going to be that size much more closely than the inductors tend to be. But you can see these things still in a lot of cords. Like a lot of cords, you'll see like, say, a cord going from your computer to your monitor, and it has that little cylinder on it. Inside that is an inductor, because what it does is it helps to get rid of any fast changing signals, any static, any noise. Because any quick changing frequencies don't have time to make it through the inductor, because if you make a quick change, the inductor says no, and it counteracts it. So only long changes get through here, and you can actually filter out noise, okay? And that's, you'll see those a lot. They filter out voltage spikes and stuff like that. So, you get a nice, better signal, a more smoothed out signal, and you can use these to even smooth out, because when you make alternating current, it does like this, and then you rectify it and it does like this. So it's all going in the same direction. And then you have a bouncing current. And so then you can take and use an inductor to smooth that out. And you basically turn that alternating current into direct current, which is what a lot of those things do, like to charge your phones and stuff do. They take that alternating current, turn it into direct current, and then you can use it in your devices. Yeah.
Is that like, I guess, similar to how when we're doing like sound, just like change gain levels?
Probably. What is the gain? I know that name, and I should feel like I should know that.
I don't know how to explain it.
You usually want to filter out higher or lower frequencies. Yes, you usually do that either with inductors or capacitors. Okay, change the capacitance, change the inductance, stuff like that. So they'll make variable capacitors that you can like move at least old school wise. They probably do it more digitally now anyway than this, but the old ways would have been like you'd have a parallel plate capacitor and you'd move it like this so that more and more of the plates got in front of each other, and you could change the capacitance and change the frequencies of your circuits to pick up different radio signals or signal out different, filter out different signals as you turn the knob. But mostly it's done all digitally now. So, okay. So here is your definition of inductance. I tend to remember it this way. It's the rate of change of flux with respect to current. All right, so change in flux per change in current, that is your inductance. And then you can use that up here to actually get an EMF. And so those are both good things. The unit for this is a Henry, and that's your inductance, okay? So this page, good page to remember, to know. And then inductance in a solenoid, we might just do that tomorrow. Oh, this is what I wanted to show you. There you go. And so here you can see the current through an inductor. Remember, the current through a capacitor started off real high and went down like that. And see how this is the opposite. It starts real low and then gradually increases. So you end up still with a time constant, which before was RC and is now L over R. Okay? So very similar. I think I'll stop there. We'll start back up right here on Friday. We'll finish this chapter up. I think there's only a few pages left. Yeah, it's just this inductance stuff and then transformers. So we'll finish this up Friday and try and do more of the questions, okay? If there's any of those example questions in particular you want me to do Friday, let me know so I can do those and, The other ones I'll just finish up outside, you know? Okay? Have a good one.